So let's go back to this tetrahedron stuff. So find the volume of the tetrahedron bounded by the planes x plus 2y plus z equals 2 at x equals 0 and z equals 0. Okay, so same thing. So if I convert this to z, bring everything over. This is that. That's going to be our surface. Okay. All right. So if I set x and y equals 0, z equals 2, so it goes up to 2 this time. If I set these two to be 0, x is going to be 2. And if I set z and x to be 0, y has to be 1. Here's our tetrahedron. Right there. So if we convert this to the xy plane, so just looking at this plane here, here's our plane, or here's our d value. All right. So it looks like we do a type 1, which is nice. So if it's a type 1, x goes from 0 to 2, but y goes from what to what? Okay. Now this is actually much easier than we think, because we could just set z equals 0, and we can solve for, in this case, y. So if we set z equal to 0, we now just get x plus 2y is equal to 2. And we could just solve for x. I mean, not solve for it, solve for y. So bring this over, and then divide by 2, we get y equals 2 minus x over 2. And that's this function right here. So now our double integral is going to go from 0 to 2, and then from 0 to 2 minus x over 2 of our function 2 minus x minus 2y dy dx. All right, so integrate respect to y. This is going to be 2y minus xy minus 2y squared over 2. So that just means that. Evaluate at 0 and 2 minus x over 2. So 0, all go 0. So let's see, we're going to have, if I plug this into here, the 2's cancel. We just get 2 minus x, okay, x, and then times all of this for y. And then this whole thing squared. And I'm squaring 2, that gives me 4. Simplify this a little bit more. Bring this in. It becomes there we go. Putting these together, finally we can simplify a little bit more. So it'll be 2 minus 2x. Yeah. That's a lot of work. All right. Good so far? I think I did my math correctly. Yeah. All right. Now we're going to take the integral from 0 to 2 of all of this dx. So this becomes 2x minus x squared plus x to the third over 6 plus, this is a u substitution. So derivative of the inside is just going to be -1. So it should be negative on the outside of itself to the third power. So it's going to be over 12. Evaluated at 0 and 2. Okay. Now we just plug in 0 is nice. Oh, some of this stuff happens. 2, plug in 2, we get 4 minus 16. Oh no, why am I doing 4? This is a 4. Crazy. Plus 2 to the third is 8 over 6. Minus plug in 2, I get 0. And if we plug in 0, all that's gone. I get a minus here. So it'll be 2 is 8 over 12. Okay, not that bad. Okay, so these cancel. This becomes positive, so I get 8 over 6 plus 8 over 12. So what is that? So that's 16 over 12. So that gives me, that's 424. Oh, nice, 2. There we go. It's kind of nice. Any questions there at all? No, everybody good? Okay. All right. So let's try this integral rule before we go to the next ones. If we try this integral here, That means we're taking the integral with respect to y first. And I actually don't know how to do that. Because we could try use u sub and u equals y squared. So then du would be just 2y dy, but there's no y on the outside, so there's no way we could use u sub. And I actually have no idea how to do this. So what we're going to have to do instead is change our bounds. Now, the problem is because we're not given a rectangle, changing bounds is going to be a little different. Okay. So first, we're going to write down what our bounds represent. So from the outer portion, x goes from 0 to 1. And then y goes from x to 1. If I draw this out, so x goes from 0 to 1 here, and y goes from 1 to y equals x. So this is the region here. And then this side, because we have in y first, we're going up this way as a rectangle, which we can't do, so we're going to have to change it to go the other way. In other words, doing the same bounds in same regions, we're going to go this way instead. So therefore, if we change our bounds, y is now going to go from 0 to 1. And remember, this is the line y equals x. So therefore, x is going to go from 0 to y. So now our change of bounds is going to look like this. So now y is going to be on the outside, and x is going to be on the inside. That. So if we take the integral with respect to x now, it's just going to be x sine of y squared evaluated 0 and y. And this is going to be y sine of y squared minus 0, because sine of 0 is 0. Well, now notice I can now integrate that with respect to y, because I have my du on the outside. Perfect. All right, so just in case you guys forgot u substitution, we'll let u equal y squared, so therefore du is 2y dy. So we just divide everything by half, and we get our portion we want. So there'll be 1/2 the integral from 0 to 1 of u, or in this case, sine of u. And the integral of sine is negative cosine. So this is negative cosine of y squared evaluated at 0 and 1 times the 1/2 at the end, which is much easier to find out. And plug in 0, you get 1, so this ends up being 1/2. So I'm not sure what cosine of 1 is, but that's what we get. So that's what I mean by changing the bounds could be a big help, because again, I have no idea how would you integrate the first part, right? And that's the process, is you have absolutely no idea how to do this. So you kind of forced just to change the bounds on purpose. So a couple things before we finish up today. We got one more problem, is properties of double integrals. Okay, so this is one very particular property of double integrals, is if we're given two regions, so like I talked about earlier, where one region is broken up, the whole region is broken into two different parts. And if you have D is equal to the union of D1 and D2, you can kind of equal them. Actually, it's supposed to be addition right here. To the addition of both integrals put together. So that was I was talking about earlier, where you can technically do an integral with respect to the x value, but you have to break up the integrals into multiple parts, and then just take the integrals individually and then put them all together. So that's one way of doing it, and you'll have no choice but to do some of those. And the next part is inequalities, right? If one function is less than the other, therefore the integrals will be less than each other as well. Now, this right here actually illustrates the type 3, or the hardest one to deal with. And you won't be seeing a lot of this in this class, but it's actually, it's part of something called the sandwich theorem, or the squeeze theorem of integration. So the last part is the most interesting part. Is not a type 1, type 2, it's considered a type 3. So if the plane is considered type 3, if, for example, we can find a boundary, values of m and n such that the integral is actually between the two values themselves. Okay, and in most cases, a lot of it is going to be sine and cosine. Okay. So, for example, let's find the integral of e to the sine x cosine x dA, where d is a disk centered at the origin and radius of 2. Okay, so essentially, this is what's happening. Right, center at the origin, and it's a radius of 2. Okay, so little precursor, not precursor, but little review of what sandwich theorem was, right? We want to figure out two inequalities that make this work, and somehow the inner is between two numbers, or some numbers we can actually take integrals of, right? So we know for sure that sine is bound between -1 and 1. And we also know that cosine is also the same way, right? Which is nice. Okay, so therefore we can put these together and say that if you multiply them each one individually, we get the same result. It has to be bounded between those two values. Okay. All right, so what we're gonna do now is since we want e to that value, we're gonna raise everything to the e power. So if we raise everything to the e power, we get that. So, and we take the integral of all of this, we get exactly this property right here. So therefore, this integral is bounded between e to -1 power times the area of our disk, and e to the first power times the area of our disk. Okay. Now the area of our disk is a circle, right? So area of a circle is equal to pi r squared. And since we're given the radius to be 2, so our area is just going to be 4 pi. So all we do is multiply both sides by it. So this is just going to be 4 pi over e, right? Just bring it down. And then e times 4 pi. So our integral is bounded between these two numbers. We don't know exactly what it is, but it's bounded between those two numbers. And that's all we can really say. So that's called a type 3. And it's basically called the sandwich theorem of integration. Okay,